All right, let's talk about a finite horizon linear quadratic regulator. First, let's break down what this title is. So finite horizon means that we have a finite window between t0 and the final time, tf. We're considering linear dynamics. The cost functions are quadratic, and the control objective is to get the final time to 0. The only constraints are the boundary is an initial condition on the initial condition on x, and the system we have to assume that the linear system is controllable. So for this control problem, we typically consider the following function. So we want to minimize u in the state space or in the control space, whole reals of p. Let me take that back. Oops. So we'll minimize p, which is equal to 1/2 T transpose TF P x of TF, all right, plus 1/2 times the integral of T naught to TF, right, the finite time horizon, plus the integral of x transpose QX plus U transpose RU. All right, and now we're going to make this subjected to the dynamics, and we can consider a time variant system, and the initial condition x naught. The matrices Q and R and P are given. We need to find where Q is semi-definite, semi-positive, definite, and R and P are positive, definite. And they're all symmetric. All right. All right, so then now if we use the state equations, co-state equations, the optimal control conditions, and the transversality conditions, we want to use those. So we want to create the Hamiltonian and put it in the form that we saw last video. So that means that the cost function is now given by, so we got capital phi. This will be equal to 1/2 x transpose TF PF x of TF plus nu transpose of the initial conditions minus x at T naught minus x naught. And then we got the Hamiltonian H. This will be equal to 1/2 x transpose QX plus 1/2 x transpose RU plus lambda, which is one of our costates, AX plus VU, which is our dynamics, right? All right, so now let's walk through those equations that I listed before, 1 through 4. Number 1, again, is the state equations. right? And that'll be given as x dot is equal to the partial of the Hamiltonian, partial lambda, and then that transpose. That'll be equal to ax plus bu. Make sense? All right, the next one is we're going to look at the costates, or costate equations. All right, and that's our lambda dot. And this will be equal to minus partial of h with respect to x transpose, which is going to be given, which is, if we come back up here and look at the partial derivatives of x, we've got x in two places. We've got x in the first component and the last component, right? So then if we take the partial derivative with respect to these two, to h, we'll get x transpose. Well, we'll get, using the transpose, we can just do x transpose q plus lambda transpose a. And then this whole thing will be transposed, which will be equal to qx plus a transpose lambda. Oh, and negative. There should be a negative there too, right? Negative and negative. All right, next, let's look at the optimal control condition. All right, this will be partial h, partial u, transpose is equal to 0. This implies that we get RU plus B transpose lambda is equal to 0, which implies that U is equal to minus R. Oops. And remember, we can take the inverse of R due to the positive definiteness of it. Let me go back a couple more. There we go. This implies that we get that U is equal to minus R inverse B transpose lambda. Okay, so now we have our input that we want to determine is the input that we found is dependent on the costate, right? So that means that we have to figure out what our costate is to get an optimal control solution. The last one is the transversality, if I can spell it right, condition. Right, and so this means that we have lambda at the final time is equal to the partial of phi, capital Phi, partial of x at the final time, transpose, which is equal to just pf x tf. Great. So now if we combine all of these guys, we've got, so we have dynamics here, we have dynamics of our state, we have dynamics of our costate, we've got an input relative to our costate here, and we've got initial and final conditions. Initial conditions on the state. Up here, if you go back, we have initial conditions in our problem statement here, and we have initial final conditions due to the transversality conditions on the costate right here, PF of X to TF. Okay, so now we can put this into a larger system. So this implies, let's make this prettier, great. So this implies that we can get X dot, we can just take the stack of them, and this will be equal to A, and then on the right we have B, R inverse B transpose, okay? On the bottom here we got negative Q, and then we got minus A transpose. Erase that guy. Okay, and then we got X lambda. With initial conditions, X naught, and final conditions of lambda. equal to PF x TF. All right, and so now since lambda is the adjoint of a linear system, x, and lambda TF is equal to P x TF, then the form of this relationship holds for all time between T naught and TF. So that means that we can find a solution, lambda TF is equal to P of T times X of T. Okay? So then let's take the differential, running out of space. So let's take the derivative. One. All right, let's take the derivative. Again, lambda T naught is equal to P of T lambda, or X of T. We're going to take the time derivative of this. So this will give us lambda dot is equal to P dot, because it's may change with time, plus P x dot. Okay? So then this implies that because of our, if we go back over here, our not our transversality, but our costate equations, we have a costate equation for lambda dot here. So let's plug that in. So that gives us negative Q x minus A transpose lambda is equal to P dot x plus P times the dynamics of our system, transpose lambda. All right, now let's expand this guy. Right, so yeah, so now let's plug in Qx minus, let's plug in Px for lambda. And then now we have that we only have a function, we only have an expression with respect to x, and we remove the lambda, right? Px on the right. Great. Right, so we've inputted for lambda here, we inputted Px, and for lambda here, we inputted Px due to this expression here. Great. All right, so now if we move all the terms to one side, we'll get the following. We'll get P dot plus PA plus A transpose P minus PB R inverse B transpose times P plus Q. And then this will be equal to, times X is equal to 0. All right. So now we get a condition on P that we'll need to satisfy. So namely that P will have to satisfy the following. P dot plus PA plus A transpose P minus P B R inverse B transpose P plus Q is equal to 0. And so this guy right here, this expression, this big guy right here, this expression, oops, too big, is known as the Riccati equations, or continuous time Riccati equations. All right, and then these are widely studied in the literature. And then also note that because of our definition of lambda, so due to our definition of lambda, the controller, which was equal to u, is R inverse B transpose P, transpose lambda, right, is equal to minus R inverse B transpose PX. So now we've recovered we've basically essentially removed the costates from our system, but gained a P matrix instead. So what do we do next? So now the problem is transferred from solving for this P matrix for all times between T naught and TF. And so next what we can do is we can take this. So next we can take an equivalence. P is equal to two matrices, U and V, the inverse, where these matrices satisfy the following. So we get U dot, make that bigger, U dot, and V dot is equal to A minus B R inverse B transpose, A transpose, and on the left, Q, negative Q. This will be equal to U and V. Okay. For the case where U at the final time and V at the final time is equal to I and PF. All right, and so now for this matrix, which I've given you, in a graduate course, you would do a little more background on why this matrix is given. But in this class, I'm just going to state it for you. So note that the boundary conditions are chosen such that the P at the final time is equal to V at the final time times U inverse at the final time, which is obviously PF, right? And then next, note that, so let me make a little bullet here. First note that, then note that P dot is equal to V dot U inverse plus V U dot inverse. And then, as an aside, note that for any matrix, any square matrix, this holds, right? So then if we take the derivative, the time derivative of this, assuming that U changes, we'll get U dot U inverse plus U inverse dot is equal to 0, which implies that U dot inverse is equal to negative U inverse U dot U in times U inverse. And then also U inverse U is equal to I, results in the same thing. All right. So I'm going to block that off just as an aside, and come back over here. So now, if we come back with the expression for the derivative of the inverse of u, then we get n and p. Then we'll get the following for the derivative of p. We'll get p is equal to qu minus a transpose v u inverse minus u v times u inverse au minus br inverse b transpose v u inverse. Kind of squished up there. All right. Which then through some mathemagic results in p dot is equal to negative q minus a transpose p minus pa plus bp pb r inverse r transpose p. So now this recovers the algebraic Riccati equation as well, which therefore we can define the Hamiltonian matrix, which is capital H here, as equal to A minus Q, negative B, R inverse, B transpose, negative A transpose. Right? And so then if H is an LTI matrix, then the solution of U and V can be defined as the following. Well, it's pretty basic, right? So U of T, just using the exponential matrix, is equal to exponential of H T minus F, as you would expect, times U TF V of TF. So backwards propagations. And thus the expression for P, and as a result, the expression for U can be obtained for all time between T naught and TF as U is equal to R inverse B transpose V U inverse X. So remember, this was our P before. So now we have basically a backwards propagation here, where we have the final times of V and U, and V and U defined for all time using this basically a state transition matrix, such that once we do this, we can find the initial times for, well, we can find U and V for every time step and make our input relative to those time steps times the state. So that's pretty cool. All right, next is the infinite horizon, which is similar to the finite time horizon. So the infinite horizon LQR, or linear quadratic regulator, right? So this problem is, so the finite horizon is what we looked at before, that had a final time that the solution had to adhere to. This is an infinite horizon, so there's no final time. You're just looking at it as t goes out to infinity. So that requires a bit of a different notion. So basically, we want to ensure that the limit as t goes to infinity of the derivative of p is equal to 0, which then will imply that 0 is equal to q plus a transpose p at infinity plus p at infinity a minus p infinity b r inverse. B transpose P at infinity. And so this guy is just called an algebraic Riccati equation, different from the differentiable or the differential algebraic Riccati equation. All right, and so this equation you can solve it for given R and Q. You can solve it directly for P naught. Similarly, the expressions for U and V can also be used, where P at infinity is equal to the limit of V U inverse T as T goes to infinity, and such that the controller can be defined using this matrix. So then we get U is equal to R inverse B transpose at P infinity times X. And so then but it's worth noting that the control designed for both the finite time and infinite horizon, LQR, linear quadratic regulator, is done through the choices of Q, R, and PF, right? And then remember that the Q, R, and PF came back from our cost function, right? And so recall that the cost function is x1/2 x transpose T transpose f of t, p at the final time, right? xtf plus 1/2 times the integral t naught to tf x transpose qx plus u transpose r u dt. So that means that our matrices f, q, and r are given. pf, q, and r. All right, and so now it behooves us to find p overall over the time horizon, and that's what we did using the different matrix modifications and multiplications. All right, that's all I got.